Okay, hi everyone. This is the last heat and mass video that I'll be doing for homework 5 and the last heat and mass video that I'll be doing in general for this semester. So today we're going to be talking about heat exchangers. So the main part of today's video is to look at the heat exchange rate and derive this equation, and then look at co-current heat exchangers, which means that they run, the streams run in the same direction versus countercurrent where they run in opposite directions. And then we're going to be looking at the log mean temperature differences. And that's the format that we're going to have the heat exchange rate be derived into. And then secondly, we're going to be looking at heat exchanger effectiveness and then how that corresponds to and works in conjunction with NTU and the C min over C max, or concentration minimum maximum ratio for sizing. So I just have my page here. This just has the agenda on it, as you'll see. So we'll start by drawing our example problem, and we're going to look at co-current first. So a co-current heat exchanger. So heat exchangers are going to look like cylinders, and it's basically going to be a smaller cylinder within a bigger cylinder. So there's going to be some sort of hot liquid running through our middle cylinder here. And then on the outside is the colder fluid running through. So we'll have some sort of temperature of the cold current in, temperature of the cold current out, and then temperature of the hot current in, and temperature of the hot current out. So this is kind of what our problem looks like. I only drew one arrow at the end, but the cold current is also flowing out that direction as well. But essentially on that outer cylinder, that outer perimeter is going to be cold fluid, and then the inner one is going to be hot fluid, and we're going to have some sort of related cross-sectional area here, where we're looking at how that is flowing within that area. And the whole point of the heat exchanger is for there to be heat exchange amongst the hot current and the cold current. So that hot current is going to influence the cold current and make it warmer. So therefore, the temperature of the hot current going out is going to be cooler than the temperature of the hot current coming in, because the whole point is to exchange heat from the hot current into the cold current. So that final temperature of the hot current coming out will be cooler because it'll be losing heat energy to the cold current. So we'll just have this arrow here. So, yeah. So when we write this equation, we're going to be looking at some sort of flow here, heat flow represented by Q, and that's going to be equal to capital U, which is going to represent our universal heat coefficient or thermal coefficient, and then that'll be looking at how the temperature of the hot is going to the temperature of the cold, and then we'll also need to look at this over that certain area that we have here. So this is just our equation for showing how this heat is flowing, and the temperature is going to be going from the hot to the cold, and then we're looking at this over some certain area here with that universal heat coefficient coming into play. So usually when you would try to solve this equation that we've written here, you would typically just, take the integral of that because you have that derivative there, but we can't quite do that yet. So the reason why we can't take this integral yet is because We know that as we move through the system, the temperature of our hot stream and the temperature of our cold stream will be changing, but this integral would be taken with regards to a changing area, and we do not have a relationship between the change of the temperature and the change of the area quite yet. So we can't fully encompass the changing temperature by taking the change in area. So we have to make some sort of relationship between those two. So first I'm going to backtrack a couple steps and write out this relationship here where we can say that the mass flow rate of our hot stream times the heat capacity of our hot stream is going to be equal to that mass flow rate heat capacity relationship, which we're going to represent by a capital C H. So this CH is representing the mass flow rate heat capacity of hot stream. So this is just an important relationship for us to have here before we continue to try and simplify this and develop a relationship between temperature and area. So we can do the same thing for our cold stream. The mass flow rate of the cold stream times the heat capacity of the cold stream is equal to that mass flow rate heat capacity of the cold stream. So these are just two relationships, and we'll see how this comes into play in just a second. And then we can recall the equation from general chemistry where we said that heat, or Q, is equal to the mass flow rate times heat capacity times a change in temperature. This equation should look pretty familiar to you. This one right here should look pretty familiar to you because that is a fundamental relationship in chemistry. And then you'll probably notice right above here we have mass flow rate times heat capacity. So we can substitute that in and get some sort of heat relationship for both our hot stream and our cold stream. So we can say that Q of the hot stream is going to be equal to the mass flow rate heat capacity, aka capital CH, times a change in temperature. And then same thing for the cold stream. So we now have this relationship for both our hot and cold stream for that heat with the mass flow rate heat capacity variable here and then the change in temperature. So now we can come back to our main equation and begin to plug these relationships in and start to derive this thing. So we have, if we want to substitute in, sorry, this is going to be, I need to take the Q relationship one step further. So we have these in terms of a changing heat. So dQ is going to equal heat capacity times dt. And then same thing here. Sorry, I had to squeeze that in a little bit, but over here you can see this relationship right here. That change in heat of hot and cold equals this here. So we're going to plug in that relationship, but at its most general state over here. So we're going to have dQ is equal to U times change in temperature times change in area. So this is what we have to start. We've taken those integrals away because we can't quite do that yet. And we're just taking the derivative of this equation here. And then I combined the temperatures into that delta T figure there. Now we're going to look at what the driving force for change of our temperature is going to be. So driving force for change, that's represented by a D of our change in temperature. So what is the driving force for the delta T? What is our driving force for change? What does that equal? And that's going to be equal to the change in temperature of our hot stream minus the change in temperature of our cold stream. So I've written this term here, this TH minus TC as delta T in this equation. And then now we're expanding this out to say that the change in the hot temperature stream minus the change in the cold temperature stream is equivalent to that derivative of delta T. And so we know what these two equations are represented by. That is what we've derived over here. So we actually have this equation. We just have to rearrange this a little bit in order to get it in the correct terms. So we can say that dT of the hot stream, as we found over here, is equal to the change in heat over the mass flow rate heat capacity of the hot stream. And then same thing for our cold stream. The change in temperature of the cold stream is equal to the change in the heat flow over the mass flow rate of the heat capacity of the cold stream. So I've just rewritten that over here to be actually in the terms that we want, and now we can plug this in over here. So we have d delta T is going to equal change in heat over mass flow rate of the heat capacity of the hot stream over change in heat over minus change in heat over the mass flow rate heat capacity of the cold stream. And then there's one thing to tweak with this equation. So in order for this to be in the correct units, we have to put a negative sign in front of our change in heat of the hot stream, because we know that the temperature of the hot stream is going to get colder as it goes on, so it therefore needs to be negative to account for that. So this is what we have here after plugging that in and adding that negative sign. And now we're going to factor out dQ. So we have the driving force for the change in temperature is equal to our negative change in heat times 1 over mass flow rate heat capacity of hot stream and mass flow rate heat capacity of the cold stream. So this is what we have here now. And then we're going to plug in this equation up here for dQ down here. So now we'll get that the driving force for change in temperature is equal to negative universal heat coefficient times change in temperature times derivative of the area, all multiplied by 1 over the CH minus 1 over CC. I'm probably going to refer to it as CH and CC from now on, just because mass flow rate of the heat capacity of the stream is kind of a mouthful. So I'll just say that probably from now on. But this, oh, I forgot to close my parentheses. This is what we have, and now that we have substituted that relationship back in. So now what we can do is divide over our delta T in order to get like units on the same side, and then now we can take the integral. So if we do that, we're going to get 1 over delta T times d delta T equals negative U negative 1 over CH minus 1 over CC times dA. And when we take this integral, we will notice that U and this whole term here are all constants in comparison to the A integral. So you can keep these as constants and keep them outside of the integral. So this makes this pretty easy. And to solve for this, we can recall that 1 over whatever that integral is going to be equal to the natural log. So we will have the natural log of delta T, which is equivalent to the natural log of delta T at our final position, which we are going to label as position 2, divided by our change in temperature at position 1. And so what that delta T means is that we're looking at the change in the hot temperature and the cold temperature at position 2 for the numerator, and then for the denominator, we're going to be looking at the change in the hot stream at 1 minus the hot stream at, or minus the cold stream at 1. So even though it's two different streams, we're looking at just that position So the change in temperature at position 2 will end up being the difference between the hot stream and the cold stream. And then same thing for position 1. And then this will equal negative u times a, because the derivative of 1 is going to be equal to whatever variable that is, so there will be an a there now, times negative 1 over ch minus 1 over cc. Alright, so now we have developed this relationship here, and now we're going to go back over and look at these equations that we had derived before, and now we're going to change them into terms of ch and cc. So if we solve for that, we're going to get that ch is going to equal ch is going to equal q over change in temperature. And this one's going to be negative, and then cc is equal to q over delta t as well. So if we plug this relationship in, we'll get natural log of change. So like I said, the change in temperature 2 is going to be equal to temperature of the hot stream at 2 minus temperature of the cold stream at 2 divided by, and then for change in temperature at 1, that's going to be temperature of the hot stream at 1 minus temperature of the cold stream at 1. And then that is going to be equal to, I'll show you what that looks like right now. So that's what that looks like. And then this is what solving for ch and cc looked like. And now we're going to plug that back in over here. So we get negative ua. And then since it's 1 over ch, the q will now be in the denominator and delta t will be at the top. So we'll end up getting delta t, and this delta t, since it's relating to the hot stream, this is going to be the change in the hot stream at 2 minus 1 this time, because this is only looking at the hot stream. So we'll have t of the hot stream at 2 minus t of the hot stream at 1 divided by q minus t of the cold stream at 1 minus t of the hot stream at, t of the cold stream at 2 over q as well. So then this is what that relationship will look like. So I plugged in the t's there at positions 1 and 2 for the cold and the hot stream, and then the q is now on the bottom because the original fraction was inverted. So this is what our simplified equation looks like so far. So lastly, what we can do is simplify this a little bit by pulling those temperatures back into, summarizing them back into a delta T instead of having them expanded. And then we also want to solve this equation in terms of Q, because that's what we're looking for, is that heat exchange rate, which is Q. That's how the heat is flowing, the rate. So we need to solve for Q. So the first thing I'm going to do when I rewrite this natural log is I'm going to change this back into change in temperature at position 2 over change in temperature at position 1 equals negative UA, and then I'm going to pull out 1 over Q from our parentheses so that it makes it easier for us to solve in terms of Q. And then in the parentheses, the temperature of the hot at 2 minus the temperature of the hot at 1 minus the temperature of the cold at 1 plus the temperature of the cold at 2 is going to be equal to the change in temperature at 2 minus the change in temperature at 1. Because we are including both the hot and cold stream currents at both positions of 2 and positions of 1. That's how that relationship will summarize. So now we have this, we have condensed our temperature changes and then pulled the Q out. So now we're going to solve in terms of Q. So we'll have Q equals negative UA, and then that'll be multiplied by change in temperature at 2 minus change in temperature at 1, all over the natural log of that relationship of change in temperature of 2 over change in temperature at 1. So this is what we will get as our simplified equation here now. We've solved in terms of Q, and this is actually going to be our log mean temperature difference equation, LMTD for short. That's what this is that we've solved for here. So now I'm going to talk a little bit more about the differences in the relationships for this, depending on whether it's co-current or countercurrent. So the way I'm going to represent this is visually by a graph. So this is going to be our co-current heat exchanger, and then our countercurrent heat exchanger. So I've just drawn these little graphs here so that we can look at this. So when we were looking at our co-current heat exchanger, we said that the temperature of the hot stream was super hot here and the temperature of the cold stream was cold, right? So I'm going to put this here, hot, cold as H and C. And then at position 2, we know that our hot stream gradually got colder because it was exposed and exchanging its heat energy with the cold stream. And then vice versa, our cold stream got a little bit warmer because it was exposed to that heat and started to heat up a little bit here. So we'll notice that at position 2, our change in temperature between the hot and the cold streams is pretty dang low. So that means that when we plug that into this equation, this is going to be a low number, which means that our Q, our heat exchange rate, is not very good. It's going to be pretty small. So our co-current heat exchanger is not our ideal heat exchanger design, because we want as much heat exchange rate as possible. And that's kind of where the effectiveness comes in here of whether co-current or countercurrent is better. So now let's look at our countercurrent. So a countercurrent heat exchanger, I'm just going to draw it right underneath here. So that's once again the cylinders, and then with the smaller cylinder with the hot in the middle. We're going to have our hot current flowing down towards the right end, and then our cold current is going to flow the opposite direction. So just to give you a little visual of what this looks like, we have our hot stream flowing towards the right, and then our cold stream flowing towards the left. So they're going to be counter current, going opposite directions of each other. So when we're at position 1 for our hot current, that's still going to be pretty hot. That's at position 1 still. And then for position 2, our cold stream, that's where it's going to start. So that'll start at a cold temperature down here like it did with the co-current, but now it's at position 2 starting there. And as it's exposed to this hot current, it's going to get warmer and warmer and warmer. So our cold current will begin to get warmer as it approaches position 1. And then as our hot current approaches position 2, it's going to get a bit colder. So it's going to start to go down. So we have our cold current starting pretty dang cold at 2, because that's where it's beginning. And then as it approaches 1, it's being exposed to this pipe of hot current, and it'll start to warm up here. And then vice versa for our hot current, it's going to start here pretty dang hot, and then it's exposed to all of this cold current here as it travels to position 2 and gets gradually colder. And you'll notice that this change in temperature is much bigger than that of the change in temperature from the co-current heat exchanger. So this is going to be a larger change in temperature. So when you plug this in, this is going to be a bigger number, and we're going to get better heat exchange rate. So that's kind of commenting on the effectiveness of co-current versus countercurrent heat exchanger, showing that the countercurrent is going to be better because it'll have a larger change in temperature. So now we're going to look at effectiveness. If we start to look at it numerically, so we've already decided that the countercurrent is going to be a better format, but now we want to look at the effectiveness of like finding the ratio of whether having a minimum or a maximum mass flow rate heat capacity is better or worse. So when we're looking at effectiveness, I'm going to represent that by a curly E. That's going to be whatever Q we actually have in our system divided by Q of like the ideal version, which would be the maximum Q that we could get. So this is kind of similar to efficiency. That's like you have the actual heat transfer rate that you have versus what could be the maximum. So that's pretty similar to like efficiency, saying what percentage, like how close are you to the actual maximum, the actual best exchange rate that you could get. And that's what our effectiveness is here. And then we can recall that we had defined this in terms of our, kind of hard to see it now, but in terms of our mass flow rate heat capacity for both the hot and the cold stream right here. And that's kind of what we want to look at now, because we want to decide whether the maximum mass flow rate heat capacity is better or minimum. And we're going to write this out in terms of both our hot and our cold stream. So when we think about our heat exchanger, if we have our hot stream going really, really, really fast and our cold stream going really, really, really slow, this is going to be our best case scenario for exchanging heat between these two streams, because since the hot stream is going to be going really fast, that means that our CH is going to be really big, which means that our delta T is going to have to be really small. So that means that it's going to be hard for our hot stream to cool down, meaning that it will stay hot for longer and therefore be able to exchange heat with the cold stream for a longer time. And then it's vice versa for the cold stream. If it's going really, really slow, then our CC, or our mass flow rate heat capacity of the cold stream, is going to be smaller, which means that our delta T has to be much bigger, which means that we're going to have a more effective change in temperature of the cold stream, which is what we want in this scenario. And then if we did it the opposite way, we had our hot stream going really slow and our cold stream going really fast, then that's probably, the heat exchanger is probably more meant to cool down the hot stream rather than to heat up the cold stream, because it will be easier for the cold stream to stay cold for longer due to its speed, and the hot stream to be affected by the heat exchange of the cold stream much more because it's going slower. So hopefully that makes some sort of sense, but now we're going to rate this. Efficiency for our hot stream, we know that Q is going to be equal to our C delta T. So for the hot stream, we'll have our C of the hot stream times our delta T, so that's going to be our temperature of the hot stream at 2 minus the temperature of the hot stream at 1, or final position. Actually, I'll just say temperature of the hot stream going out minus temperature of the hot stream going in. Wait, I think that will actually be opposite. That'll be temperature of the hot stream going in minus temperature of the hot stream going out. And then on the bottom here, we're going to have C min, because we know that in order to get the best heat transfer, we need that to be a minimum, because we need the speed to be at a minimum. And then that'll be the temperature of the hot going in minus the temperature of the cold going in. And then we can write the same thing for our cold. We'll have C of cold is going to be T cold in minus T cold out. And then on the bottom we'll have the C minimum, T cold in minus TH in still, the hot going in first, T cold in. It will actually be our T of the cold going out on the numerator minus the T of the cold going in, because we want to heat up that stream, so it's going to be hotter at the exit point rather than the entrance point. So this will be that efficiency relationship for both the hot stream and the cold stream here. So now, what is NTU? So I had mentioned this at the beginning when I talked about our agenda today and how it's related to effectiveness. So NTU is going to stand for net transfer units. So this essentially means what is going to be the net transfer between the two streams in your heat exchanger, aka how can you optimize it. And that's going to be equal to our universal coefficient of the heat energy transfer times the cross-sectional area divided by the mass flow rate, heat capacity. So C, and then this is going to be C minimum, because we know that minimum is going to be our optimal case for best efficiency. So usually when you buy a heat exchanger, you're going to be given the UA, so you're going to be given your numerator there. And in order to optimize your heat exchanger, since you know what the given is and you want to make NTU as best as possible, because that's going to be the net transfer, how much you're transferring between the two streams, you can solve for the minimum mass flow rate heat capacity using these up here. So you have a way to solve for C min if you rearrange all of this and then solve for all those numbers. So that's kind of how effectiveness is related to the net transfer units. So lastly, we're going to talk about that C minimum, C max ratio. So if you have C minimum over C maximum, you're going to know that the minimum is going to be equal to either your hot or cold stream. So whether you want to be making your hot stream colder or your cold stream hotter, that will decide what the minimum is. So if you're wanting to make your cold stream warmer, then your hot stream will be your minimum and your cold stream will be your maximum. And then vice versa. And so this ratio, I've just written it here just so you can see, can also be related to our NTU because you have a C minimum in there. And that kind of tells you about which stream you're wanting to look at and you're wanting to really optimize by changing the temperature the most that you can for that stream. So the whole consensus here is that NTU is going to be a function of your efficiency and your C minimum, C maximum ratio. Because in order to solve for your NTU, you're going to have to use your efficiency here to solve for the C minimum, and then you also need that ratio in order to know which stream you want to be drastically changing the temperature of, and that kind of tells you what needs to be C minimum, what needs to be C maximum. So that's going to be everything for today's video. So we did talk about co-current and countercurrent and kind of solving the log mean temperature differences for these two systems. So we got our equation for heat exchange rate, and then we also looked at which one was technically better as a heat exchanger, whether it was co-current or countercurrent, and deducted that countercurrent would be much better because it results in a greater temperature difference. And then we also looked at effectiveness of our heat exchanger and comparing which stream needs to be really fast and which stream needs to be really slow, depending on which stream you want to drastically change the temperature of. So that's going to be everything for today.